Hello, good afternoon, everyone. I'm Kira Zeidelman, Senior Manager at NARUC's Center for Partnerships and Innovation, and I want to welcome you all to today's webinar on the reliability considerations with increasing renewable energy generation. So if we could go to the next slide. NARUC represents state regulatory commissions that are responsible for regulating electricity, natural gas, telecommunications, and water utilities in all 50 states and territories. My team, the Center for Partnerships and Innovation, on the next slide, is a grant-funded office dedicated to providing technical assistance to NARUC members by connecting state regulators with expertise and strategies to navigate emerging challenges. So if we could go to the next slide, we will get into today's webinar. I first want to thank Debbie Liu and Libby Jacobs for recommending the excellent panelists that we'll be hearing from today, and the U.S. Department of Energy Office of Electricity for supporting this webinar series. We have a lot to discuss, so I'll now introduce our moderator, the Honorable Kim O'Gwyn, Commissioner with the Arkansas Public Service Commission. Commissioner O'Gwyn was appointed to the Arkansas PSC in 2016 and serves on NARUC's Executive Committee and Board of Directors. She is Chair of NARUC's Task Force on Emergency Preparedness, Recovery, and Resiliency, and is a member of NARUC's Committee on Energy Resources and Environment, International Relations, and the Washington Action Committee, as well as the DOE-NARUC Natural Gas Partnership. We thank Commissioner O'Gwyn for leading this important conversation, and I'll now pass things over to her.
Thanks, Kiara. Good afternoon, and thank you all for joining today's webinar on balancing the clean grid, reliability, and renewable energy. This is such a timely topic, and we have excellent panelists. Across the U.S., renewable wind and solar generation resources are making up a growing segment of energy and capacity. In the SPP and ERCOT markets, renewable generation, excluding nuclear, averaged more than 25% in 2020, and often edged up to provide more than half of the power supply multiple times throughout the year. We are likely to see continued growth as the U.S. Energy Information Administration estimates that solar, wind, and energy storage will account for 80% of new electric generation coming online in 2021. State regulators, utilities, and market operators share responsibility for grid reliability and are currently thinking through what this growth in renewable generation means for system reliability. In late May, the North American Electric Reliability Corporation, also known as NERC, released its 2021 Summer Reliability Assessment, showing an elevated risk of summer energy emergencies in New England, the Mid-Continent ISO, Texas, and the Western Interconnection, and a high risk in California. Customers in these regions could experience energy shortfalls on normal and above normal peak demand days this summer. The factors contributing to NERC raising alarm for the upcoming summer seasons are numerous, complex, and regionally specific. While increased renewable generation is by no means the main culprit, the growth of variable inverter-based resources does present new challenges for energy grid operators in different areas of the country. What makes power grid reliable? Can inverter-based renewable resources perform those essential reliability functions? If not, what should regulators and system planners do? Today, we will hear from experts in energy reliability on how regulators can meet these issues head-on and plan for a clean and reliable energy future. We will start with a 5-minute introduction, opening statements from each of our 4 experts. Then we'll move into questions. The audience members are encouraged to submit questions in the Q&A box in your webinar toolbar. I'll share these with the panelists towards the end of the webinar. We'll start with Mark Alstroms, who is the VP of Renewable Energy Policy at NextEra Energy Resources and NextEra Analytics Incorporated, and also the president of Energy Systems Integration Group. Mark serves on NERC's Reliability Issue Steering Committee and has worked for almost 2 decades on the reliable integration of variable generation into power systems and markets. Earlier, he was a founder of 2 software companies. He's also the president of the board of directors of the Energy System Integration Group, the nonprofit Technical Collaboration Association for engineers, system operators, researchers, and policymakers working on our evolving energy systems. We welcome Mark. We'll go next to Julia, and I told her that if I'm certain about her last name, I'll just call her Julia from ERCOT, as she says she is very well known by. She is the lead planning engineer of resource adequacy at ERCOT. Julia primarily works on system flexibility, frequency control, and performance issues related to high penetration levels of inverter-based generation. Her other interests are integration of storage and distributed generation. Julia serves on a number of technical advisory committees for broad projects related to high penetration of inverter-based generation carried out by NREL, EFRI, NERC, and others. Julia is a chair of the High Penetration of Inverter-Based Resources Task Force at ESIG and vice chair of NERC's Inverter-Based Resource Performance Working Group. After Julia, we'll hear from Drake Bartlett, who is the Senior Market Operation Analyst at Xcel Energy. His primary job responsibility is to help Xcel Energy integrate higher levels of renewable generation while minimizing costs and maintaining system reliability. And last, we welcome Sheila Tandon-Mans, PhD. She's the Director of Decarbonization Planning at GE Energy Consultant. She'll deliver the final opening statements. Sheila leads GE Energy Consulting decarbonization practice, bringing over 15 years of technical and business strategy experience with GE Global Research and GE Renewable Energy in wind and solar energy. Prior to joining GE, Sheila earned her CPA as a financial auditor with PricewaterhouseCoopers and her PhD in electrical engineering from the Massachusetts Institute of Technology. Please join me in welcoming our expert panelists. I'll now turn the floor over to Mark and invite Julia, Drake, and Sheila to follow. The floor is yours, Mark.
Thank you so much, Commissioner. It's a pleasure to be here. I'm going to just kind of lay some of the groundwork for the excellent speakers that follow here. We're all good friends, been working together in this space for many years. You know, we've all heard the adage that we tend to overestimate the effect of technology in the short term and underestimate the effect in the long run. And whether you think that was said by Bill Gates or Arthur C. Clarke or many others, I think it's good to remember here, because in the present, in the short term, you know, it can feel like a slog. You know, we're trying to bring together fairly complex, you know, regulatory and policy and technical issues. But when we look back on it, say by 2030, looking back, I think I'm very convinced actually that we'll realize that we see the arc of a wonderful transformation toward a more elegant solution. In this case, a more elegant, cleaner power grid for society that will become clear. So my message is don't be afraid of the technology in particular. If we apply this really to the grid more generally, you know, we've had 100 years to get used to conventional resources. So today, you know, most of us look at that and we say, well, you know, that's pretty simple, pretty good. You know, if you actually pull out the individual components of the resources, the conventional resources, and you look at them more carefully with fresh eyes, you actually realize that they have a lot of quirks. You know, if we were looking at them the same way we're looking at these new renewables, for example, we'd say that, you know, it's not easy to use these to make a reliable system out of these sorts of parts. But, you know, we get comfortable with that. We understand it. We come up with the ways of making it seem simple. The same will become true with renewables. But 20 years ago, when renewables were just starting to come on the system, like with early wind in the early 2000s, and especially with distributed resources, you know, the initial impact was, well, that's kind of a nice curiosity. It's still kind of expensive. But when something actually happens, like a disturbance on the grid, we just want you to get out of the way. We don't want you to be interfering with the processes that we have in place for the last 100 years. About 10 years ago, though, at NERC and at the utilities, you know, we started seeing that this stuff is getting real. And we got concerned about what became known as the essential reliability services discussions at NERC in particular. And at other places around the world as well, I would point out. And Julia has a lot of experience globally on these issues as well. So Julia and myself and others, we spent literally 5 years of our life at NERC on the Essential Reliability Services working group. And really, we started to try to tease out to say, well, what are the characteristics, the services, the important pieces coming from these resources that are necessary to maintain a reliable grid, especially a reliable bulk power system overall. And we realized that, these are questions that have never really been seriously asked before, because you didn't really have that much of a choice with conventional resources. You kind of, had what you had. They weren't easy to modify. They weren't reprogrammable. They weren't digital for the most part. So we kind of dealt with what they gave us. But if you step back and you say, well, if I were going to start from scratch, ideally, what would I really like to have? And that's what I think we started with some great work at NERC on the Essential Reliability Services and the many reports that came out of that. Now today, another 10 years forward, we're really in the thick of this. It's a fascinating time because we're actually having very serious discussions across the board on what exactly do we want, because now we actually can get it. This work is being done at many places. I'll point out just a couple. One is NERC is continuing this work at the inverter-based resources performance working group, which has come out with a whole series of wonderful technical guidelines and guidance on how we're dealing with these new digital electronic devices and how they're going to fit into the bulk power system. And also at ESIG, the Energy Systems Integration Group that was mentioned, we have many task forces and working groups, and we're part of a global power system transformation, getting the best practices from around the world on this. ESIG is a cool place to do that because it's kind of a place where the techie groups get together under Chatham House rules, more or less, to kind of just share their experience, their mistakes, their findings, their new studies, and kind of work out the best practices and pathways we want to take. And really, there's a lot going on because we're rethinking resource adequacy. We're rethinking exactly what do you want to have happen after a disturbance event. It's rethinking market design, operations, planning, the role of distributed energy resources. All of these things fit together into this transformation that we're talking about here. And the key point that I like to make is that, the digital revolution has finally really hit the power sector. Given enough energy, electronics, software, and storage, we can emulate whatever kind of machine we want to have connected to the grid at that point. So it's kind of like your iPhone. You think of it as, well, that's a great piece of hardware. Most of the iPhone actually is software when you think about it, right? Which means it can be programmed. And we now have the capability to do that. But you have to figure out, okay, what do I want before I can actually, program it appropriately. At this point, many of you are also saying, well, that's great, but this technical stuff is complicated. It looks like a black box. It's kind of, it's kind of scary, right? And I'm fascinated personally by this interaction between the technology, the policy, the regulatory world. Because I want to emphasize to everybody here that when things, quote, get technical, that's a good thing. That's a really good thing, because it means that we have great teams of people that are defining the space and the possible solutions. And interestingly, it's almost never about needing a great next breakthrough to do what we want to do, to meet a objective of society in this case. It's much more common that we actually have 12 different ways of doing it, and we have to sit down and talk about the trade-offs, the coordination, which approach will we take? Because obviously we're putting this all into a highly interconnected grid, so it takes a lot of coordination and decisions, and that has to bring in the vendors, how we're going to, make these be standard products, how we're going to use them in planning, operations, and during all types of emergency situations as well. So we're really trying to select the good pathways, and so this is a positive. It's more about coordination than it is breakthroughs, are key points to take away. And I think that we have to look at this, that the technology, the policy, and the regulatory sides are all kind of pressing on this problem space from their own side. And we hope that a few years from now we'll come out with a very elegant way of meeting the needs of society that satisfies everybody. And it takes all of us to be working together as a team to make that happen. So let me just close by just bringing it back to some of the latest news from NERC. I'm on the Reliability Issues Steering Committee, which is a high-level kind of strategic advising committee to the NERC board about what should the NERC priorities be for the next 2-year period. Every 2 years, we do a survey, we have a major workshop, and we come out with a a key report called the Reliability Risk Priorities Report. That report is actually out for public comment right now through June 23rd. And if you don't have access to it, just send me a note. I'd be happy to get you the link to it so you can review it and provide comment. It will then go to the board of directors after the next revision and be approved by the board probably in August. And it sets kind of the priorities for NERC for the coming period. I was actually asked to lead one of the 4 main pillars there in that report, the one on grid transformation, which is kind of all encompassing. And it's really talking about the pathway from here to the 2030 timeframe. How does that affect the role of NERC and the bulk system planning, and how it's going to bring in more and more distributed resource participation and so forth. The other pillars that are also important. One is on extreme events. Another is on security risks with cyber and so forth, and another on critical infrastructure priorities. But it also brings together all of the other attributes here of, I'm going to share my webcam. There we go. I don't know why it didn't share. Also brings together all of the other aspects that are tracked by NERC. So in closing, I think this is a great thing. NERC is, I think, doing a very good job on this. And I think when we do look at back what we're doing today and over the next couple of years by 2030, we will see that we are evolving at a digital pace, but we're actually doing a very good job of moving in the right direction, and we'll come out with an elegant solution, even though it appears to be a little bit complicated and messy in the short run. So with that, I'll leave it, and I look forward to the discussion.
Am I going next? I had one slide to talk over, so I wonder if we can share it. All right, here it is. So I wanted to cover more of a technical, so Drake will be talking about resource adequacy, capacity challenges. I wanted to just focus more on technical challenges that we're seeing with some of it is because of more inverter-based resources. Some of it is just because of where inverter-based resources are being developed. So probably you all know inverter-based resources are being developed where there is good potential for wind and solar. So our system is a good example, and we're seeing a lot of development on the edges of our system. So as Mark mentioned, over the years, these resources have developed capabilities to provide some of essential reliability services that we've previously seen from conventional synchronous generators being provided. But we are pushing limits of our system even further, and we are seeing encountering issues related to weak grid and voltage stability issues due to long distance high power transfer. And this is again because of where generation is being developed and because of long distance to load centers where this generation needs to be used. And so we're seeing need for this inverter-based resources to continue develop the technology and continue being part of the solution, which starting to understand bits and pieces of what we need, but we're finding ourselves in this kind of circular problem. That's my favorite cartoon here is, and we as a system operator are here, and we're finding it challenging to require some of the products from inverter-based resources because they are not yet commercially available and they have not been yet sufficiently developed. So currently, the way we deal with technical challenges, we develop operational constraints. And these constraints are not your regular thermal constraints on transmission lines. These are stability-related constraints, and sometimes they are on number of transmission lines. That adds level of complexity. Limits on these constraints are changing with operating conditions. And you can see here over time, we are having increasing number of these stability constraints that we need to manage. So what these constraints do to inverter-based resources, it leads to curtailment, because if inverter-based resources behind constraint, they cannot deliver their full capability. Again, here you can see amounts of installed capacity of wind and solar. In blue is wind and yellow is solar, and increasing amount of curtailment percentage that we see compared to what could have been delivered. This, in turn, results in shrinking markets for inverter-based resources for OEMs. On the other hand, manufacturers are telling us, it's inverter-based resource. You can do a lot of things with controls. So tell us what you need and tell us what you want. And so this circle kind of closes. And as Mark mentioned, there is a need for collaboration on developing these new products and services to address changing system needs. The services need to be delivered by inverter-based resources, and they can be part of the solutions. There are pilots out there where inverter-based resources are providing more services than they are today. I think everybody could benefit from the solutions being harmonized and standardized, because it will be extremely expensive for manufacturers to develop products if requirements for the services are different in different areas. For some of the services, probably economic incentives are needed in terms of new market products to incentivize the services and development of the services, because even though capabilities are maybe already available, developers only asked for what they can earn revenue from, and currently the services are not paid for. And so collaboration between all different stakeholders is needed more than ever. And we're looking to work with manufacturers, with policymakers, with organizations such as NERC, producing standards for this new capabilities and services as we're going forward. With that, I want to pass it on to Drake.
Thank you, Julia. Next slide, please. So I want to start on the left side of this slide, which shows the state of Colorado in blue and 3 energy resource zones, which are labeled ERZ1, ERZ2, and ERZ3. The energy resource zones are geographic regions in Colorado with good wind and solar resource and access to PSCo's transmission system. The yellow shading represents locations with existing wind generation. So now I want you to turn your attention to the upper right-hand corner of this slide. This bar chart shows that Energy Resource Zone 1, the left-hand bar, has about 1,400 megawatts of wind generation. Energy Resource Zone 2 has about 2,500 megawatts, and Energy Resource Zone 3 has less than 300 megawatts of capacity. So Public Service Company's current wind generation portfolio has just over 4 gigawatts of wind generation capacity dispersed among these 3 energy resource zones. Okay, now let's focus on the main graph in the center of the slide. This graph shows the capacity credit that we would give to new wind generation added to our existing Colorado system. The acronym ELCC stands for Effective Load Carrying Capability, which is a mathematical method for determining a reliability-based capacity credit. So the vertical axis shows the ELCC, or capacity credit, expressed as a percentage for any new wind resource, and the horizontal axis shows the volume of incremental wind expressed in megawatts. The colors represent the location of the new wind generation. Yellow represents new wind in ERZ3, red is new wind in ERZ1, and blue is new wind in ERZ2. The solid lines represent the average capacity credit, while the dashed lines represent the marginal capacity credit. For example, let's say that we decide to add 1,000 megawatts of new wind generation to Public Service Company's system in ERZ3. So we would move along the x-axis to 1,000 megawatts and then move up to the solid yellow line to see an average capacity credit of about 27%. That means I could count on 27% of the 1,000 megawatts of new capacity, or 270 megawatts of firm capacity to meet my peak load obligation. On a marginal capacity credit basis, which is represented by the yellow dashed line, the 1,000th megawatt of new ERZ3 wind would only receive a capacity credit of about 17%, which coincidentally is about the same marginal capacity credit for adding the first megawatt of new wind generation ERZ1. This makes intuitive sense because once you add 1,000 megawatts of new wind resource to ERZ3, then ERZ3 would be approaching the same level of installed capacity that currently exists in ERZ1. Okay, so there's 3 big takeaways that I want from this slide. So takeaway number one, as you add more renewable generation, in this case, we're looking at wind generation, the ELCC or capacity credit declines. A very common mistake that I've seen from RTOs is that they assign a static capacity credit in their resource planning process to any new renewable generation. This isn't realistic. As you add more renewables, the capacity credit should decline. Takeaway number two, the marginal rate of decline in capacity credit is much steeper at lower levels of renewable penetration. So RTOs or balancing areas who don't have experience with high levels of renewable generation are the least likely to account for this declining capacity credit, but they will experience the biggest reliability impact of assigning a static capacity credit. And then takeaway number three is resource diversity matters. Adding new wind generation in ERZ3, where PSCO has the lowest volume of existing wind generation, clearly provides a higher capacity credit than adding wind generation in ERZ1 or ERZ2. So this slide only shows the declining capacity credit associated with incremental wind generation. However, solar generation and energy storage have similar patterns of declining capacity credit as penetration levels increase. Next slide, please. PSCO is currently engaged in electric resource plan proceeding, and this slide shows the capacity makeup of the company's preferred generation portfolio, which would achieve an 85% reduction in carbon emissions by 2030 relative to 2005 levels. So starting with the bar on the left of this bar chart, you can see that the top three categories, which are energy storage and demand response, wind generation, and solar generation, make up almost 12 gigawatts of installed capacity in PSCO's 2030 preferred portfolio. But as you move to the bar on the right side, you can see that that 12 gigawatts of installed capacity translates to about 3.5 gigawatts of firm capacity to meet our firm capacity need of 8.7 gigawatts. So I will now turn it over to Sheila. Next slide, please.
Hi, everyone. Sheila Tandon-Mans here. Thank you for having me on this panel today. As Commissioner O'Gwyn mentioned, I'm from a group called GE Energy Consulting. We're a small group of technical and economic consultants that serve clients around the world, utilities and grid operators like Drake and Julia's, and globally as well. We also serve GE equipment businesses in order to help them integrate their equipment, whether it's gas turbines or wind turbines, onto the grid. And so as a result, we have unprecedented access to all sorts of grid problems globally. We've enabled about 70 gigawatts of wind, solar, and batteries to be interconnected into the grid globally across 20 countries. Folks on the team right now are fighting the fight while I'm here sharing insights with you. So what I figured I would do is try to kind of pull together what Mark, Julia, and Drake talked about. Clearly, the problems are very real and very deep. And so the question is really, how do you pull it all together since there's so many moving parts? And that's really what we're seeing as a consulting group, is really that need for holistic planning, given that renewable penetrations are really pushing the limits of our systems. So what I figured I would do here is maybe just show you some really interesting real world data to highlight what we're working on. So what I'm showing here in these three graphs on the left are three different systems. So Julia's, Drake's, so Julia's, ERCOT, Drake's, Public Service of Colorado, and a third one, CalISO. And for each of them, what I'm showing is what was the wind and solar penetration for 2020 on an hourly basis for the whole year. And so what you can see is that, you know, ERCOT was on average 25%, PSCO 35%, CalISO 30%, but that's not where the story ends. They may be average, say 30%, but on an hourly basis, it's very variable. And so for example, in ERCOT, you can see that I have the star there, which basically highlights how, despite being on average around 25%, ERCOT in 2020 hit 60% wind and solar penetration. For PSCO, that was 83%. For CAISO, that was 80%. And if you were to ask them in this panel, they'll tell you that those numbers keep going up. Why does this matter? The reason why this matters is historically, planners have been focused on the worst case scenario planning, which is usually peak demand. So what I've shown here is kind of this shaded bar in the middle of the picture, which is really your summer peak. And if planners are focused on that summer peak, as we are transforming the system with greater amounts of renewable energy, there are new worst case scenarios to plan around. And so planning around peak by itself will miss part of the reliability picture. And so that's really my first message on the right side is that as a consulting practice, we are starting to support our clients with respect to what are those other peaks that utilities and grid operators need to worry about, given that we're constantly pushing the envelope with penetration. Another example of a worst case scenario that we're increasingly working on is shown by those triangles on the graph. So what those triangles are is what I'm calling here a max down ramp. So if you were to take the derivative of those green dots, how rapidly is renewable penetration changing within an hour or within even a sub-hourly interval? And so what I've highlighted with the triangles is what was that maximum down ramp? Why am I saying down ramp? Well, if renewables is falling, do I have the resources I need on the system fired up and ready to go to fill in the gap? And can they fill in fast enough? So in ERCOT, for example, taking the derivative of this graph, you can see that the max ramp was on Christmas Eve at 5 p.m. ERCOT went from 45% wind and solar to 25 in 1 hour. And that corresponded to about a 7 gigawatts drop. In PSCO, it was 60 to 30 in May at 9 p.m. In CAISO, it was 55 to 30% in November. So you can see that focusing on peak misses some of these other dynamics that are going on. And so that's really the first message, new peaks to plan around. And I could spend a whole hour talking about the other ones that we're thinking about, but just wanted to give you two to start off with. I mean, the other dimension here, and this is really what Drake was looking at, is now how do I plan around the uncertainty of each of those? So not only do we have to plan for, say, peak renewables and peak ramping, but the uncertainty around those and the uncertainty and coincidence. What if they happen during an outage? What if they happen during high load or during extreme weather events? So that's the other dimension there. The other area that we're really seeing an increased need for in terms of our support of clients is really bringing that picture of the physics that Julia is talking about together with the adequacy and the operations planning practices that Drake is referring to, and really looking at that holistically. Because every time we make a change in the system, as we're going to these higher levels of penetration, both the physics and the operations change simultaneously. And one of the challenges that we find in terms of supporting our clients is really almost a human one. The departments that do the planning are often siloed. And we even find that within our own teams. You've got the physics folks sitting there speaking physics, and you've got the economics people sitting there speaking dispatch and economics and marginal cost and all of that. And there isn't a lot of interface. And in many cases, that interfacing is not even really allowed because their planning practices are heavily regulated. And so I think one of the messages I wanted to share today is, in terms of this audience, is that as regulators, you are in a really great position to facilitate those barriers to change. So what are you seeing in terms of the utilities you work with? Are you seeing them siloed? Do they need to be working together to really plan the physics and the operations? So I think that's probably one of the top messages, is how do we evolve those planning practices, and who asks utilities and grid operators to evolve? I think regulators can play a really strong position in that. The other elements here in terms of physics and operations is really, in these situations where renewables are high, synchronous units may be low, and they may not be available to support some of the really basic physics needs like voltage and frequency. So that's an example of how the dispatch conditions on the grid can actually affect the physics. And then at the same time, if we're going to replace those synchronous units with inverter-based resources, can those inverter-based resources bring new controls, and controls that we can rely on, so that we can rely on them and displace synchronous units? So just the last message is really about how there's no one size fits all. I picked these three systems because they're three very different systems. ERCOT has more wind and is a deregulated system and is essentially an electrical island. PSCO is a smaller system that's vertically integrated. And CAISO has a lot more solar in their system. And you can also see in terms of these pies on the chart, CAISO really doesn't have coal. So they may not have some of the constraints that come with coal units. So every system is different. Every system has their own sort of cards they've been dealt, so to speak. And so when we're trying to really address some of these challenges, there isn't a one size fits all. And our message is usually about unlock the cheapest enablers first. So, Drake already referred to using diversity of resources as a way to bring in more reliability into your system, siting wind plants all over the place, balancing wind with solar with offshore. Another one is integrate the demand side into this picture. That's a way to unlock more flexibility in our system. And then the last point is, if there is a new service that we need on our system, are we paying for it appropriately? Have we defined the right market products or the right grid codes in order to ask for some of the new, say, controls that we might need on this system? So, just some thoughts very briefly. I know that was a lot, but hopefully gives you a picture of how we're really looking at this holistically. The physics, the operations, not just peak, but all hours matter. And really, it's about unlocking the cheapest enablers first before you start putting new assets into the grid. So with that, I'll pass it back to Kiera and Commissioner O'Gwyn. Thank you.
Commissioner, I think you're still on mute.
Statements, and I will encourage our audience to use the Q&A to submit questions. We'll just jump right into our questions. The NERC CEO did a briefing for our NARUC Gas Committee on June the 14th, and he expressed his concern about the rapid pace of changes coming to the power grid as the bulk power system becomes more decarbonized, decentralized, and digitized. So the question here is, how can we gain a better understanding of these trends and their associated complexities and risk? And I'll just allow you all to jump in as you see fit. Mark?
Given the NERC pseudo guy here, I guess, no, I think Jim Rob makes good points, and I think NERC overall is doing an excellent job of exploring this space. It's interesting that we're talking here a lot about renewables and storage to some extent, and I do think that that Drake made good points about diversity, but that diversity also extends beyond renewables into the conventional fleet and into the codependencies between all pieces of this, especially when we get into extreme events, storm events. Codependencies with the natural gas system is a big issue at NERC right now because of what we've seen recently in some of these things, and the cyber risk as well. So, diversity is good. I think we're just looking, and NERC, I think, is doing a good job of helping to guide people to focus on how do we make sure that the renewables are good citizens of the grid, all the way from the interconnection requirements that Sheila mentioned, up until the planning, the operations, the disturbance response, how we're substituting or maybe less conventional synchronous inertia with the faster response of these new resources. So we actually need less of the conventional synchronous inertia because now we have much faster frequency response after a grid disturbance. Things like that all come into play. But he makes good points. I think NERC has come to a really pretty well-balanced view of this, though, about how we're just trying to make everything plan and work together. As Sheila said, it's this overall coordinated planning and collaboration between all of us that's so important to make this work.
Anyone else would like to respond to that question?
I can add to that maybe. I think one of the keys is understanding of how all these resources are working. So to Drake's point, it's okay that you have more installed capacity than what you can expect across peak, as long as you understand what you're going to expect across peak. And so we are seeing in ERCOT more and more working on producing different scenarios of what may happen, on looking also not only at inverter-based resources, but also at synchronous generation. And so for example, one of the scenarios we're looking at is increased number of outages on synchronous generation. And we have scenarios like low wind, low solar, and high load because of high temperatures. So we're starting to look at more scenarios, and I think overall we headed towards probabilistic assessments of resource adequacy. So I think that's the way it's headed with uncertainty of renewable generation.
Sheila or Drake, would you like to respond? Okay, Drake, I know I can't see your face. Okay, we'll move to our next question, and it's on electrification. Does electrification make system balancing and reliability with high renewable generation more or less challenging? And what do we need to do to address the issues?
I can jump in there.
Okay.
I think that for us, electrification and bringing in the demand side is the next frontier. So we essentially have been working on this frontier, which is bringing renewables from pretty much zero to 30% on average. That journey took us about 15 years in terms of our practice. Now we're at a point where getting from 30 higher is now about bringing in the demand side. And so electrification allows us to not only clean up all the stuff that people are using, whether it's their cars, their hot water heaters, we can, plug that all in and ensure that the electrical system is clean. That's a way to take carbon out of the system, but it gives us another lever. We can now put in price signals to help match up usage with all those excesses of wind and solar that I was showing on my plots. It's another lever that we can use. So it's actually, I'm not saying it's easy, and the journey we've been on in terms of wind and solar to date has not been easy either. But it's the way we're going, and we're going to do it. And our team has been enjoying fighting the fight to get here.
Any follow-up?
Yeah, maybe can add. I think for us, challenge would be to forecast what's coming in terms of load, so that we are ready for it and we can assess resource adequacy going forward. But as Sheila mentioned, I think there is also flexibility that's locked there, and introducing market products that can help us unlock this flexibility and use this load demand response. It can be for ramping products, for ancillary services. It can be very flexible as long as we find a way to use it.
Great.
Okay, and so the next question, and I'm going to try to combine two questions. So the next question, we'll talk about inverter-based generation. And how do you balance that between the supply side and the demand side? And additionally, can you all talk about the limits of inverters to deliver that equivalent spinning inertial reactive power? So who would like to start on that issue?
Yeah, maybe from system operators perspective, I can start. We've been seeing increase in inverter-based resources over the past 10 years, and it's a relatively rapid increase, but we're learning a lot with, we're doing a lot with forecasting and with situational awareness. Having forecasts even closer to real time so that we can be prepared to balance. One of the examples I can mention, we are using now short-term wind and solar forecasts in our 5-minute economic dispatch for generation. So we know what's going to happen in the next, or trying to forecast what's going to happen in the next 5 minutes with wind and solar. So that gives us more flexibility and makes us more prepared for what's coming. In terms of services that inverter-based resources can provide, not only inertia, it can be also frequency support and voltage support. Also, a lot has been developed over the past 10 years. We've reassessed needs for inertia and for frequency response. We recently introduced fast frequency response product that invites resources such as basically any inverter-based resource can participate if they design they product correctly and comply with our performance requirements. In terms of inertia, currently, that was one of the points I was trying to make. Currently, there is no widely commercially available technology to provide inertia from inverter-based resources, but it's been shown in a number of pilots that controls can be designed to the point where inverter-based resource, from inertia perspective, behaves similarly to synchronous generator. One more level of flexibility there, that inertia contribution can actually be changed. So if you have physical synchronous machine, it only depends on mass of the machine that you already have, and you cannot change it. Whereas in inverter-based resource, depending on storage that you have behind inverter, you can actually vary amount of inertia that they're providing. So technology is developing. It's out there. So now manufacturers are coming to us and telling us, you tell us what you need. But we also need to find a way to incentivize it so that developer goes and procures this kind of products.
I would just add that I think Julia is being modest here because she's deeply involved in grid forming inverter work right now, which is kind of this next step about the next generation of inverter technology. And she was kind of alluding to that with her slide, but you don't need every resource out there to do everything for you, but you need to have enough of the services, right? The other place that that renewables have actually done a lot more than people recognize is that, well, wind has been providing dynamic, ride through and dynamic voltage support for years, going back to, what was it, FERC 661A, Sheila? And more recently, there have been work orders so that all inverter technologies that are connecting to the bulk power system now are required to provide dynamic reactive support for controlling voltage, as well as providing primary frequency response. And ERCOT actually started that earlier too, where all the wind in Texas, in ERCOT, is providing primary frequency response just like any conventional generator.
And solar and storage.
And solar and storage, right, exactly. So I think there's broad support from all these new technologies to be excellent citizens of the grid. We can actually do things that we couldn't imagine we could do with conventional resources, and that's what we're trying to figure out with the current technical proceedings.
Yeah, I'd just like to add one thought, and that is, when Mark was speaking, he was alluding to the NERC committees and talking about how you can reimagine the system, from scratch and not be stuck in the way we've always done it. And just to point out that the concept of inertial response is very much a mechanical generator concept. that we've always counted on inertial response to provide what we're looking for is some kind of fast frequency response, where when we have a sudden change in frequency, we have a response to address that change in frequency, usually a sudden drop in frequency. But and with mechanical generators, that historically has been an inertial response, where the spinning mass of those generators, that inertia provides that check on the drop in frequency. But inverter-based resources, right? They don't have that spinning mass, but they can respond really fast. So just bringing that up as, you know, what Mark was talking about in terms of rethinking how you think of these essential reliability services.
And that's what the ERS work was really keying on. Like what, you know, was that, you know, we need certain responses. We need certain things to support the grid when something happens, but it doesn't have to be done the same way by all resources. And if you've got these lightning fast electronic and software devices that have the right controls, you know, as we talked about, there's actually a number of ways you can do this and be grid supported. So thanks, Drake.
We have a question that came in from the Q&A. We do have an audience of regulators today, and so I'm going to ask you all these questions on how can regulators help utilities get more comfortable with using distributed and demand side resources to meet grid needs. Do you have requests or suggestions for commissions to facilitate better integration of demand side resources at the scale required to offset VREs, I'm sorry.
Well, I'll start briefly. I mean, the real concern, or at least you know, what NERC, for example, is working on a lot is just kind of how do we know what's out there, you know, so that it can be modeled as part of the system plan. Because NERC has overall responsibility for the reliability of the bulk power system, which actually includes the effect of distributed, you know, the distribution systems upon the transmission system. So a big part is just kind of keeping track of what's there, what version of inverters are there, so that it can be at least in aggregate modeled appropriately, so that we can understand how the rest of the system is going to work. Now, clearly with FERC Order 2222, it's a big issue right now about how can you actually aggregate that and get additional services up to the bulk system as well. And there's complexity there, and that's going to take, I think, a lot of coordination, collaboration between these different silos. You know, a lot of state jurisdictional distribution system issues, and obviously we don't want to harm the reliability of the distribution system as we try to provide services to the bulk system. But it's all technically possible. It's just a lot more data, a lot more parties, different concept of how we're going to aggregate that together and still have trusted levels of service performance at both the distribution system and the bulk system or up at the market. I guess that's not a solution, but that's kind of the problem statement, right?
Yeah. Any additional?
You know, one of the things maybe I can add, we as ERCOT, we don't have jurisdiction, for example, to require from distributed resources to have certain technical capabilities, and they certainly can have them, and they can provide certain services if they have these capabilities. And then, so one of the things is to mention is IEEE 1547 2018 version of a standard that, for example, currently haven't been yet adopted in ERCOT area. And so if that standard, and that would be Public Utility Commission's assignment, I guess, to decide what technical requirements should be for distributed inverter-based resources. And so if these standards are adopted and we know how these resources are behaving on the grid, we can better design services where they could participate.
So let's talk about tips or lessons learned so far. And so what tips or words of wisdom would you have for developing countries that are dealing with or preparing to deal with reliability issues because of the increased renewable generation?
I can start as a plug for Mark, and you know, Mark mentioned, or Commissioner O'Gwyn mentioned that, you know, Mark has been a huge part of a group called ESAID, what does it stand for now?
Energy Systems
Energy
Integration
Systems
Group,
Integration.
EC.energy on the web.
Yeah, it's evolved over the years, and I would say that we've worked with clients, in developing countries that are really trying to think about how to scale their renewable energy needs. And one very sort of low-hanging fruit way to kind of overcome some of those hurdles is to get involved with these industry groups. That really helps you understand that many of the best practices have already been addressed. It doesn't, like I said, every system is different, but at least you realize that many of the challenges have already been addressed by other system operators. And clearly the relationships are collaborative, and you learn from others. And I think that's a huge way to get started. The other is also to engage consultants like us who can come in and bring a fresh perspective on your system, to really, we're not entrenched in your existing processes. We're not, we don't have to do things the way are regulated in your system. We can bring a fresh perspective and look at the system and figure out, what are some of the tools in the toolbox that you haven't considered yet. And so that's often a role that we play, is to do those holistic studies that in many cases those grid operators or utilities maybe can't do themselves, because perhaps it's a little too prickly. There's often politics involved, and so it's sometimes a better way to do it is to bring someone from the outside in, that has credibility to help facilitate some of those barriers to change.
If I may add a little bit here, so there was a recently created organization called Global Power System Transformation Consortium, and I think that's an excellent venue to learn from. So this organization that was founded by 6 system operators. It has research organizations from around the world involved in it, specifically from countries that face a lot of inverter-based resource integration, so such as Germany and Australia and California, Texas, great land of Texas, so there is a pillar there that's meant for countries that are only now starting to develop inverter-based resources, and that offers a lot of learning opportunities and experience sharing, where system operators that have already a lot of experience with integration of inverter-based resources are either sharing resources or providing some kind of webinars that people can learn from. So there's a good resource for everybody, not only countries that are just starting to develop inverter-based resources.
So I would say two pieces of low-hanging fruit. The first would be good forecast of your renewable generation, right? So if you don't have a good forecast, it's hard to get your hands around the variability that these resources can bring to your system. And the second, also associated with variability and uncertainty, is try to maximize the flexibility of the balance of your generation portfolio. So the more flexible that portfolio is, and by flexibility, I mean the ability to turn generation on and off quickly, the ability for those generators to ramp quickly or have larger ramp ranges. All of those improvements in flexibility will allow you to accommodate higher levels of variability and uncertainty without having to curtail the renewable generation, which you're obviously trying to accept as much of that renewable generation as possible.
And transmission. I mean, you showed, Blake, even the diversity within the state. We need more intra-regional and I think national high voltage transmission to really get to these higher penetrations at an economic and reliable manner for all citizens. And we have to figure out how we're going to build a lot more of it. So thanks.
Yeah, maybe if I can add just a little bit to this, both points, kind of looking at our experiences of countries that already implemented it. Some of the things, if you can foresee how much is coming, some of this can be done better in the holistic kind of way, what Sheila was talking about. So if people look more ahead than just 4 or 5 years, and then if they believe that amount of inverter-based resources will continue to grow to the amounts that we are seeing, then maybe better, more optimal transmission decisions can be made in advance.
Right.
And just to complement that, I think the way we say it is plan before you build, which sounds so kind of simple and trite, but what we're finding is a lot of policymakers mandate a certain build out for other reasons, and so it's actually built before it's planned, or mandated before it's planned, and sometimes that takes some cards off the table in terms of the value of diversity and technical diversity and that kind of thing.
So one more thing to complement what Mark was saying about transmission. If you can expand the geographic area around which you're trying to perform your balancing function, so in other words, for a small balancing authority area like Public Service Company of Colorado, joining a larger organized market would expand those boundaries, and that makes geographic diversity of resource help you out, as long as you've got the transmission capability to move that around. And it gives you the ability to utilize your transmission system better. So if that's an option, enlarging the area of concern for system operations.
For example, Northwestern Energy just joined the EIM this week.
Yeah.
So.
Yeah. Well, thank you all. Of course, we can go another hour on this discussion. I did not think that I would be able to leave a renewable energy integration panel without talking about transmission. So, Mark, great inclusion there. Thank you all for participating in today's webinar, and thank you to our attendees for participating. And I'll turn it back over to you, Dominique.
All right, thank you all panelists. I will take over just to give out an announcement here quickly. Just for the next webinar, it will be, this is a changed time, so please, if you did sign up for this webinar already, please make sure your calendar is up to date. This webinar, Virtual Power Plants in the 20s, it is moved into August 12th from July. I also wanted to make an announcement about the NARIC Summer Policy Summit. It will be a hybrid meeting. It will be in Denver, Colorado, in person, July 18th to the 21st. Kira, did you want to mention that at all?
No, just encourage everyone to take a look at that. It is a hybrid meeting, so we do have virtual attendance options in addition to in person in Denver, Colorado. So hope to see a lot of folks there, either virtually or in person. Thanks, Dominic.
Great. All right, if you have any questions, reach out to me. There's my email. We also will be posting this video to our website on the Innovations webinar page. Thank you so much. Have a good weekend.